Hello again. Here's the next problem, an optimization problem. This too is borrowed from web work. The question is, how far from A should the point P be so that this angle has the highest value? So we are maximizing the angle theta. And the P is a variable. This point varies from A to B. At some points it gives you a smaller theta, at other points gives you a larger theta. So we're going to use derivative to find the location of P where this angle theta has its highest value. So first we need to use, first let's visualize this, and then we use some trigonometry to set up a function that we need to maximize. So here is a picture of different locations where P can be. Some places have bigger angle, some places lower angle, and there are infinitely many points to choose from, but only one of them is where the maximum angle occurs. So let's look at this problem with placing our variables in. We want to maximize theta as a function of x. What is x? The question is how far this point should be above the floor for this angle to be maximum. So we need theta as a function of x. So how do we relate theta to x? Notice that these two triangles are right triangles, and we know everything there is to know about right triangle trigonometry, right? So in this, let's look at the top triangle. One side is 2. By the way, if we say P, this point P, is x units above the bottom of the picture, then the remaining distance should be 3 minus x, because it was given that that whole side is equal to 3, and if you add these two you should get 3. The x's cancel out. So, and these are right triangles, and we can use right triangle trigonometry. So one way, there are different ways you can work with this. I'm going to use a fact from geometry that if you have two parallel line and a transversal line cutting the two, then corresponding angles are equal. So if I draw a horizontal line from here, it would be parallel to the top line, so that makes this angle equal to this angle. Let's call it alpha. So this two would be alpha. And on the other hand, the bottom line is parallel to that dotted line. So if you call this angle beta, then that is equal to this angle. And then we can see theta is alpha plus beta. Why do we do this? Because in this right triangle, I know two sides. I mean, not by knowing they are labeled as some variable or some constant. So those two, the 2 and the 3 minus x, relate to alpha through triangle trigonometry, and in this case tangent. Tangent of alpha is the opposite over adjacent. The opposite is 3 minus x divided by the adjacent 2. And that's equivalent to, we need to solve for alpha. Alpha equals to inverse tangent of 3 minus x divided by 2. So we know all about inverse functions, right? When you have tangent of alpha equals some value, it's the inverse tangent of that value should be alpha. Similarly, beta, for beta I can say tangent of beta equals x divided by 5, and that's equivalent to saying beta is arctangent or tangent inverse, as you like, of x over 5. So now I have alpha in terms of x, beta in terms of x. What did I need to find? I needed to find theta in terms of x. And theta is alpha plus beta. So now I'm ready to set up my function that I am maximizing. So I can write theta equal to arctangent of 3 minus x over 2 plus arctangent of x over 5. And this is the function that we are maximizing. So from this point on, the problem becomes a routine. So first we use a picture. This is a typical optimization problem. If there is a picture, we use it to relate variables and then set up a function that you're optimizing. In this case, we want to maximize this function. By that, we mean find the right x that would make this quantity the highest possible value. And x varies between 0 and 3. So here at the bottom, x is 0. At the top, x is 3. So x is between 0 and 3. And we're looking for an x between 0 and 3 that makes theta the highest possible value. How do we find maximum? Now, this we will talk about whether setting this equal to 0, gives us a critical number. At that point, you either have a local maximum or a local minimum. But apparently in this problem, it would be a maximum, which can be verified. We will talk about it later. So to find a maximum of any function, just like the previous problem, we know at the local max, the derivative, in this case is theta prime, has to equal 0. That's where the maximum is. So we find the derivative of theta. So from this point on, the problem is computational. So I hope you remember the formula for derivative of arctangent and also the chain rule. So derivative of arctangent is 1 over 1 plus the square of its argument. But not just that, because there is also a chain rule that says you have to multiply by the derivative of the inside. derivative of 3 minus x over 2. I hope you don't use the quotient rule for that. The reason you don't need to use the quotient rule, it's much easier than that, because the denominator is constant. And this one can be written as 3 halves minus 1/2 x. And derivative of that is exactly minus 1/2. And then plus derivative of the other arctangent, which is 1 over 1 plus its argument squared, x over 5 squared, times derivative of x over 5, which is just 1/5. And now we set this equal to 0. That's what we have to do. We set it equal to 0. And then solve for x. That's what we do. So let's simplify this. Here I can write this. So I don't need to repeat theta prime. I just work with that expression on the left side of the equation, and the right side is 0. So let me switch to different color. All right. So here on this side, there is a negative quantity, right? Negative half makes that negative. And the other one is a positive quantity. Now, it's easier to solve the equation. It's easier to move the one with the negative sign to the other side, meaning you add its positive, and then you write the equation this way. So for the left, I use the one with 5 in it. And then here I have 1/5. If I multiply, I can multiply numerator and denominator of any fraction by 1. In this case, my 1 is 5 over 5. If I do that, then I get 1 over, so let me find the correct space for it. 1 over 1 plus x over 5 quantity squared is x squared over 25. And now I'm multiplying this ratio by 5 over 25. Okay, then I simplified that again. So that's what that second term is. And then the negative term, the first term, moves to the right and becomes positive. Similarly, I multiply this by 2 over 2. And then on the right side, what I get is 1 over 1 plus. Now this ratio is squared. It's the square of the numerator, which is 3 minus x squared, divided by 2 squared, which is 4. And then I'm multiplying it by 2 over 4, right? 2 times 2 is 4 in the denominator, and 2 times 1 is 2 in the numerator. So this is the equation that I have so far. I can simplify it further. Multiply two fractions. You multiply the numerators together, denominators together. So in the numerator, 1 times 5 is 5. In the denominator, you're multiplying 25 by all of that. So 25 times 1 is 25. Plus 25 times x squared over 25 is just x squared. So this simplified it. And on the right, I have in the numerator 1 times 2 is 2. In the denominator, I have this quantity in parentheses times 4. So 4 times 1. Plus, when you multiply 4 by the second term here, you just get 3 minus x quantity squared. And now what? This is an equation with two ratios on the side. So I use the cross multiple method, 5 times this big denominator equals 2 times the other denominator. Another way, you're multiplying both sides by both denominators. That's how it works. So on the left, I have 5 times quantity, 4 plus quantity, 3 minus x quantity squared. And on the right, I have 2 times 25 plus x squared. So this part is just algebra. I mean, the main calculus part is right here when you set the derivative equal to 0. That's where we use concept of calculus. And of course, you cannot do anything in calculus without algebra. So you have to do some algebra at some point. Now here, if I can make my pen work. So I have a 4 here, and I hope you remember how to expand a binomial raised to the second power. You square the first term, which is 3 squared, that's 9, minus twice the product of the two. It's plus 2 twice the product, but the second one is minus x. So 2 times 3 times minus x is minus 6x. And you square the second, and that gives you x squared. And then 4 plus 9, you can write as 13, multiplied by 5. 5 times 13 is 65, minus 5 times 6x is 30x, plus 5x squared. And on the right, I have 2 times 25, which is 50, plus 2x squared. And now you gather all the terms on the left, meaning you subtract 2x squared from both sides. So this and that will give me 3x squared on the left. And then you have negative 30x on the left. And 65, you subtract 50 plus 15. And now you solve this quadratic equation. And again, you simplify one more time, divide by 3. So you get x squared minus 10x plus 5, and that's equal to 0. And this one is not factorable, so we can just use the quadratic formula. So x equals minus b. B is negative 10, so that's a 10. Plus or minus the square root of b squared, which is 100, minus 4 times a, 4 times 1, times c, which is 5. 4 times 5 is 20, and divided by 2 times a, which is just 2. And now this one you can simplify. So you get x equals 10 divided by 2 is 5. And then plus or minus. Now inside the radical, you have 80. The square root of 80 is 4 times 20, right? And 20 is 4 times 5. So the 4 comes out, becomes a 2. When you divide by 2, that 4 disappears. And then it leaves you with square root of 20. And that would be 2 times the square root of 5. Now, we got two answers. X equals 5 plus 2 square root of 5, and x equals 5 minus 2 square root of 5. What do you think? Let's look at the picture, see if both of them can be an answer. What if x is 5 plus 2 square root of 5? Does that make any sense? X, the highest x can get is 3, right? Because this side, all of it is 3, so x cannot be bigger than 3. But here we have that, so let's make a note of that. X cannot be greater than 3. So if x cannot be greater than 3, so x has to equal what? 5 minus 2 square root of 5. This is not a negative number. That should be checked, because x cannot be negative either, right? This is about half. This is, you can check it in your calculator. It's about half. All right, so that tells us something. It's about half. That means this point P is closer to the bottom, right around here, than where it's pictured. But of course, we don't know that in advance, so we just figured it out. Now, the second question is, so here's a picture of it. So x is 5 minus 2 square root of 5, and that angle is over here. That angle gives you the maximum angle. And the question is, why is it a maximum? To check whether it's a maximum or not, we're not going to do that, but we should know, because it takes a little bit of algebra, to check that theta of 5 minus 2 square root of 5, you see theta is a function of x, to check that this is a max or d max in this case, we use the second derivative test. Which means to check that theta double prime at this value x, 5 minus 2 square root of 5, is less than 0. So this is due to the fact that for a maximum, when you have for a maximum point, the concavity is downward, theta double prime has to be negative for maximum points. Okay, that's what we call the second derivative test. We already have the first derivative test we calculated above, so you just have to do one more derivative, but it requires 2 quotient rules, and it's a little bit of algebra. I'm going to skip that, not that it's hard. So that's how we know it's really a maximum. So then the question becomes, okay, so we know that's a maximum. Is there a minimum too? You see, x varies from 0 to 3. Somewhere here, it has a local maximum. Then that indicates that the minimum has to occur at the endpoints. So the question is, the minimum, the mean of theta must be at one of the endpoints. I know this question didn't ask you that, but I'm just curious. I need to know whether you have a minimum at this endpoint or at that endpoint. How do we figure this? We know theta. We just found the formula for theta, and that's what we use to find the maximum. So it's just a question of evaluating theta at 3 and evaluating theta at 0. If I do that, then I can check which one is bigger, you know. I mean, you may already know because of the angle. It looks like this is a bigger angle than that one. So this is the minimum. So you already know that. So this is the minimum. So it's clear from the picture, but we cannot trust pictures. You know, in mathematics, pictures don't prove, especially when you're measuring or you're comparing two different angles or quantities. So how do we tell? If I evaluate it at 3, what do I get? Theta, put in 3 for x. Then I get tangent inverse of 0. That's tangent inverse of 0 plus tangent inverse of 3/5, which is just tangent inverse of 3/5. The reason tangent inverse of 0 is 0 is because tangent of 0 is 0. You know, that is something we already know. And then similarly, we find theta of 0 when x is 0 at the bottom. And that would be tangent inverse of 3/2 plus tangent inverse of 0 again. And that is tangent inverse of 3/2. We know something about tangent inverse. So that from the picture, you already figured that is a minimum at x equal to 3. So the 3/5 tangent inverse of 3/5 should be less than that. And in fact, that's true, because this is the graph of tangent inverse, if you remember it from pre-calculus or here in calculus. It's an increasing function. This is tangent inverse is an increasing function. And when you have an increasing function, for higher values, you get higher values. So 3/2 is bigger than 3/5. You see, 3/2 is greater than 3/5. Let me write it the other way. 3/5 is less than 3/2, and tangent is increasing. I mean, tangent inverse is tangent 2 is increasing in each of the intervals that is defined. Tangent inverse is increasing. Therefore, tangent inverse of 3/5 is less than tangent inverse of 3/2. So the maximum, minimum. So the minimum is at x equal to 3. So that's, so the picture is really not fooling anybody. So that is really the minimum, and the maximum was here near the bottom. Okay, there are some problems from the book in this lesson that you can try. They are on this page.